In this video, I will be discussing about integrable combinations in differential equations. There are some differential equations which are very easy to find its solution if we can only right away determine the groups of terms in the equation known as integrable combinations. By correctly recognizing these terms, these integrable combinations can be transformed to an integrable function, and the solution is obtained by direct integration because these terms are exact differential. And actually, if you can recognize them, it will shorten the length of work in solving the given differential equation. So I have here a list of some integrable combinations. Number 1, x dy plus y dx is a derivative of a product x and y implicitly. And number 2, we have y dx minus x dy divided by y squared is the derivative of a quotient x and y implicitly. And also in number 3, we have x dy minus y dx divided by x squared is a derivative of a quotient y and x implicitly also. So for number 4, we have 2xy dx minus x squared dy divided by y squared is also a derivative of x squared divided by y, because if you take the derivative of this x squared divided by y implicitly, this is the answer. And we have number 5, which is almost the same with number 4, only that we have y squared in the numerator but x in the denominator here. And finding its derivative implicitly is equal to 2xy dy minus y squared dx divided by x squared. And we have here also in number 6 that y dx plus x dy divided by xy is a derivative of the natural log of x and y implicitly. But the implicit differentiation of the natural logarithm of y over x is equal to x dy minus y dx divided by xy. And we have also here the implicit differentiation of 1/2 of the natural log of x squared plus y squared here. And the result is y dy plus x dx all over x squared plus y squared. And we have a similar differential there in number 9, because if we get the derivative implicitly for 1/2 of the natural log of x plus y over x minus y, the result is x dy minus y dx all over x squared minus y squared. And lastly here, the differential of the arctangent of y over x is equal to x dy minus y dx all over x squared plus y squared. These are the most common integrable combinations that can be usually found in a given differential equation. So let's solve our problem number 1 here. Find the complete solution of this differential equation. And if this will come out in the test, you may recall your knowledge in solving a differential equation. Maybe you will ask a question whether this is a separable differential equation. But as you can notice that this binomial, which is the multiplier of dy, is a sum of x and y's. So therefore, it is very impossible for us to separate the two variables. Thus, this is not a separable differential equation. Next, we need to check whether this is a homogeneous differential equation. The first term here is having a degree of 1, and also the second term is having a degree of 1. But the third term is not of degree 1 there. So therefore, this is not a homogeneous differential equation. Next is to check whether this is an exact differential equation. So we need to find the partial derivative of y, which is the multiplier of dx, with respect to y. And the derivative of y with respect to y is 1. But the derivative of this multiplier of dy with respect to x is also 1. Hence, this is an exact differential equation. But here in this case, we will not solve using that method. We will be just shortening the length of work by recognizing some integrable combinations in this differential equation. And the presence of the integrable combination will become obvious if you distribute this dy to this binomial here. So we have y dx plus x dy plus y squared dy, and this is equated to 0. And as you can see, that this one is already an integrable combination, which can be seen here in our integrable combination number 1. So instead of writing this one, we will replace this one by its equivalent differential. So we have the differential of the product of x and y, and this is added to y squared dy, which is equal to 0. Because we are using here our integrable combination number 1. So if we take the integral to each term in this equation, we have this integration here. And we know that the integral of a differential cancels each other. So we have xy plus the integral of y squared, which is y cubed over 3. And this is equal to the constant of integration, c. And to eliminate this 3 in the denominator of y cubed, we need to multiply both sides of the equation by 3. So multiplying 3 to both sides of the equation will give us 3xy plus y cubed, which is equal to 3c. But remember that this 3, which is a constant, multiplied by another constant, is still a constant. So we can write our solution as 3xy plus y cubed, which is equal to the constant big C, which is a product of these two constants. And this is our solution to the given differential equation. So the work of solving the solution of the given differential equation was shortened by just recognizing an integrable combination in this equation here. Now let's proceed to our problem number 2. Find the complete solution of this differential equation. Now this differential equation, it is maybe very difficult to find its integrable combination. However, if you distribute this y to each term in the binomial, we have 2x y squared plus y times dx, which is subtracted by x dy, which is equal to 0. And distributing this dx to this binomial here, we have 2x y squared dx plus y dx minus x dy, which is equal to 0. And you can see that this one is somewhat like an integrable combination, which is similar to this integrable combination number 2. However, in this case, we don't have the denominator of y squared. But we have a y squared here in this term. So to have this y squared here in the denominator of that two terms, we need to multiply both sides of the equation by 1 over y squared. So 1 over y squared is the multiplier to this whole equation. So as a result, we have 2x dx plus y dx minus x dy all over y squared. And this is equated to 0. And now you notice that this is already the same with our integrable combination number 2, which is the derivative of a quotient x and y implicitly. So instead of writing this one, we will replace that one by its equivalent differential. So this is the differential of x over y, which is equal to 0. And actually this happens because we use our integrable combination number 2 here. So taking the integral to each term of this equation, we have the integral of 2x dx plus the integral of x over y, which is equal to 0. And the integral of this 2x is x squared, because the integral of x is x squared over 2, and the denominator of 2 cancels with the 2 there, plus x over y, because the integral of the differential cancels each other. So we have this sum equated to some constant of integration c, and multiplying both sides of the equation by y so that we can eliminate this y in this denominator, we have x squared y plus x, which is equal to cy. And this is our solution to the given differential equation. Now let's proceed to our example number 3. Find the complete solution for this differential equation. Now, looking at this differential equation, we may suspect that these first two terms forms an integrable combination, which is almost similar to integrable combination number 3, number 7, number 9, and number 10. Only that this x dy minus y dx don't have any denominator here, but we see a factor in this dx, which is x squared plus y squared. So when we divide both sides of the equation by this factor, we notice that we can remove this factor here at the right by dividing both sides of the equation by x squared plus y squared, and it is already obvious to see that this is the same as the integrable combination number 10 here. So instead of writing this one, we will replace it by its equivalent differential, which is the differential of the arc tangent of y over x, and this is equal to 2x dx here, because this binomial and this binomial cancels each other. So taking the integral to both sides of this equation, we have this integral of the differential of the arctangent of y over x, which is equal to the integral of 2x dx here. And we know that the integral of a differential cancels each other. So we have the arctangent of y over x, which is equal to x squared plus the constant of integration c, because the integral of x is x squared over 2, and the denominator of 2 cancels with this 2 here. So we have x squared as the integral of 2x, but this is added to the constant of integration c. So if we will take the tangent of both sides, the tangent of the arctangent cancels each other because they are inverses to one another. So this is y over x, which is equal to the tangent of x squared plus c. So, multiplying both sides of the equation by x, we have y, which is equal to x times the tangent of x squared plus c here. And this is our solution for the given differential equation. Number 4. Find the complete solution for this differential equation to x plus xy quantity times dy plus 2y dx, which is equal to 0. And the integrable combination present in this differential equation becomes obvious if you distribute this dy to this binomial here. So this is 2x dy plus xy dy plus 2y dx. And this is equal to 0. And we notice that this first term and this last term has coefficients of 2. So maybe we can group them together as 2x dy plus 2y dx. And this will be added to the middle term xy dy there. So factoring 2 outside of these two terms, we have x dy plus y dx, and this is added to xy dy. Now we notice that in this equation we have an integrable combination, the same with number 1 and number 6 here, but only in number 6 we don't have the denominator of xy. But that denominator of xy can be obtained if we multiply both sides of the equation by 1 over xy. So we have 2 times x dy plus y dx, and this will be divided by this xy, and this is added to dy alone, which is equal to 0. And you see that this is the integrable combination number 6. So using our integrable combination number 6, instead of writing this one, we will write its equivalent differential, which is the differential of the natural log of the product of x and y. And this is added to dy, and the whole sum is equal to 0. And taking the integral to each term in this equation here, we have 2 times the integral of the differential of the natural log of x times y plus the integral of dy, which is equal to the integral of 0. And we know that this integral of a differential cancels each other, so we have 2 times the natural log of the product of x and y plus y, because also the integral of the differential cancels each other, and this is equal to the constant of integration c. So this is our solution for the given differential equation. Now let's proceed to our example number 5. Find the complete solution of this differential equation. Now, so that the integrable combination will be obvious to us, let us first distribute our dx to this binomial here. So we have 2xy dx minus y cubed dx, and this will be subtracted by x squared dy if you distribute this dy to this binomial, and also minus x y squared dy, and the whole expression is equal to 0. So here we notice that this second term and the last term has a common factor of y squared. So we need to group them together. We have 2xy dx minus x squared dy minus y cubed dx minus x y squared dy, and also this is equated to 0. So factoring out the common of y squared, we have this y squared is multiplied to y dx plus x dy here. And we notice that this one is already an integrable combination which can be found in our list here as number 1. But the problem here is we have a factor of y squared. So to eliminate this factor of y squared there, we need to multiply both sides of the equation by 1 over y squared. So as a result, we have 2xy dx minus x squared dy divided by y squared. And this will be subtracted by the binomial y dx plus x dy here. And we notice that this one is already the integrable combination number 1 here. And also we notice that this is also another integrable combination which is the same as number 4. So using 4 and 1 in the list, we have to replace this one with its equivalent differential, which is the differential of the quotient of x squared divided by y. And this will be subtracted by this integrable combination, which is the differential of x and y. And this is equated to 0. So taking the integral to each term in the equation, we have the integral of the differential of x squared over y minus the integral of the differential of x times y, which is equal to 0. And we know that the integral of the differential cancels each other. So we have x squared over y minus x times y, because this integral and the differential cancels each other. And this is equated to the constant of integration c. Now, finding the LCD of these two terms here, we have x squared minus x y squared, which is equal to the constant of integration c. And multiplying both sides of the equation by y, we have x squared minus x y squared, which is equal to cy. And this is our solution to the given differential equation. Now let's proceed to our example number 6 here. So recognizing an integrable combination in this equation will not be obvious if we will not distribute our dx to this trinomial here. So we have x dy plus x cubed dx minus x y squared dx minus y dx, and this is equated to 0. And we notice that this first term and the last term here forms an integrable combination. So we group them together as x dy minus y dx plus the two middle terms here minus x y squared dx, and this is equal to 0. So these first two terms here almost form the integrable combination number 3. But the problem is we don't have this x squared in the denominator there. So the next thing to do is to factor out the common factor of x in these last two terms. So we have x dy minus y dx plus x times x squared dx minus y squared dx. And this is equal to 0. And factoring further this dx here, from the two terms, we have x dy minus y dx plus x times x squared minus y squared times dx, which is equal to 0. So that we can integrate this term here with respect to x, we need to eliminate this x squared minus y squared by multiplying both sides of the equation by 1 over x squared minus y squared. So we have x dy minus y dx divided by x squared minus y squared. And this is added to the remaining term x dx, because when this term is multiplied by this one, the remaining expression is x dx. And we notice that this is an integrable combination, the same as integrable combination number 9 here. So using the integrable combination number 9, we will replace this one with its equivalent differential, which is the differential of 1/2 times the natural log of x plus y over x minus y. And this is added to x dx, and the whole sum is equal to 0. Now, taking the integral to each term in this equation, that is the integral of the differential of 1/2 times the natural log of this quotient x plus y divided by x minus y plus the integral of x dx, which is equal to 0. And we know that the integral of the differential cancels each other, so we have the 1/2 of the natural log of x plus y divided by x minus y plus x squared over 2, which is equal to the constant of integration c, because the integral of x is x squared over 2 using the power rule in integration. Now, to eliminate these 2 here in the denominator, we need to multiply both sides of the equation by 2. So we have the natural log of x plus y divided by x minus y plus x squared there. This is equal to the constant of integration big C, because 2 times c is still a constant c. And this is our solution to the given differential equation. Now, let's proceed to our last example here. Find the complete solution of the differential equation of 1 plus the square of x plus y quantity multiplied by dx plus 1 plus x times the quantity of x plus y times dy, which is equal to 0. Now, looking at this differential equation, it is difficult for us to see the integrable combinations due to this x plus y here. So, to simplify our differential equation, we may use a dummy variable to represent the sum of x and y, say z here. So taking the derivative implicitly to each term here, we have dx plus dy is equal to dz, and that if you subtract both sides of the equation by dx, we have dz minus dx at the right hand side of the equation. So substituting these representations to this differential equation, we have 1 plus z squared, because the sum of x and y is represented by this dummy variable z, and this is multiplied by dx, and this is added to 1 plus x times z, and this will be multiplied by our dy here, which has a value of dz minus dx. So this is equal to 0. Now distributing this dx to this binomial here, we have dx plus z squared dx plus 1 plus xz multiplied by dz, because if you multiply this dz to this binomial here, we have this one, and this will be subtracted by 1 plus xz times dx, and this is equal to 0. And that is true because we multiply this dx to this binomial here. Now distributing further this one in this binomial, we have dx plus z squared dx plus dz plus xz dz minus dx minus xz dx, which is equal to 0. Now grouping all the terms having dx here, we have dx plus z squared dx minus dx from this term here, and also this term minus xz dx, and this will be added to this 2dz's term here, so plus dz plus xz dz, and this is equal to 0. And we know that this dx with this minus dx cancels each other, so we have z squared dx minus xz dx, and this will be added to dz plus xz dz. Now if we group the first term and the last term here, we have z squared dx plus xz dz minus xz dx plus dz, and this is equal to 0. Now factoring the common factor in these two terms, we have z times z dx plus x dz, and this will be subtracted by xz dx plus dz. So to eliminate the z here, we need to multiply both sides of the equation by 1 over z. So we have z dx plus x dz minus x dx plus dz over z, and this is equal to 0. Now looking at this expression here, we realize that these first two terms form an integrable combination, which is the differential of a product of x and z. So instead of writing this one, we will write its equivalent differential, which is the differential of x times z. And this will be subtracted by x dx plus dz over z, which is equal to 0. And taking the integral to each term of this equation, we have the integral of the differential of the product of x and z minus the integral of x dx plus the integral of dz over z, which is equal to 0. And the integral of the differential cancels each other, so we have xz minus x squared over 2, because the integral of x here is x squared over 2. And the integral of dz over z is the natural log of z. And this is equal to the constant of integration c. Now, to eliminate these 2 in the denominator of x squared, we need to multiply both sides of the equation by 2 here. So we have 2xz minus x squared plus 2 times the natural log of z, which is equal to 2c here. And substituting back our original variables, we have 2x times x plus y, because the value of z is x plus y. And this will be subtracted by x squared plus twice of the natural log of x plus y, which is equal to the constant of integration big C, because 2, which is a constant, is multiplied to another constant, so the product is still a constant. So distributing this 2x to this binomial, we have 2x squared plus 2xy minus x squared plus twice of the natural log of x plus y, which is equal to the constant of integration c. And combining this first term and the third term here, we have x squared plus 2xy plus 2 times the natural log of x plus y, which is equal to the constant of integration c. And this is our solution to this differential equation. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.